Now, there are two theorems that follow quite quickly from our transversal theorem. And the first one is about lines parallel to the sides of a triangle. And maybe that sounds wrong, okay? Because we go, but triangle sides aren't parallel. Let's draw a triangle and I'll show you what I mean. So whatever angles I have in the triangle, I can always rearrange, always rotate my triangle so that one of them is flat on the bottom like this. I can always have a base of some triangle. And when we talk about lines parallel to the sides of the triangle, we're talking about lines that are parallel to just one side of a triangle. So lines through the triangle like this. Draw another one up here. I can do as many of these as I want. And it may not look immediately obvious to you. So these lines here are all parallel to each other. I could even do another one up here. May not be immediately obvious to you because it's inside a triangle, but if I keep going with those parallel lines, like this, what we actually end up with is very similar to the diagram that we just had in the first class with our parallel lines. And if I keep going with the other two sides, they end up being transversals. So these slanty sides are transversals of the lines parallel to the base of my triangle. Just transversals that cross over each other like this. Transversals S and T. Okay, so in a diagram like this, we get a theorem. We get a theorem about the lines parallel to the base of a triangle. And we need to know the statement of this theorem. And we need to know how to apply it. And it says, a line drawn parallel to one side of a triangle divides the other two sides in the same ratio. Okay, so that's not exactly equal to the last theorem at all. In fact, this is a theorem that we used for junior cert if you did higher level junior cert at the end. Let's do a diagram that goes with this. So rather than having multiple lines like I've drawn here, if I just have a single line, if I have a triangle like this, and I have a single line through the triangle that's parallel to the base like this, then the theorem says that if this is in the ratio 5:2, for example, then this will also be in the ratio 5:2. 5:2. Well, what do I mean by that? Well, if I knew that this distance here was 5 centimeters and that this distance here was 2 centimeters, and then if I knew that this one over here was, say, 10 centimeters, so the 5:2 is the ratio, it's not the actual measurement. So if this was 10, then this would be 4. That's what I'm saying. Because 10 over 4 is the same as 5/2. 10 over 4 is equal to 5/2. So if this was 15, this would be 6, and so on. So that's the idea of that theorem. Let's apply it with an example. So an example to go with this. We're going to have a diagram again of a triangle. like so. Just making sure that that's on the screen. It's not. And we have a line parallel to the base of the triangle. And this length here is 4, and this length here is 3. This length here is 2, and this length here is x. So in the given triangle, find the value of x. Now the theorem that we just noted the statement of, and by the way, we must learn that statement. We don't need to learn the proof, but we do need to know the statement. Sorry, I'm after smudging that. Okay, so we must find the value of x here. So I've said that the ratio here, 4 is to 3 or 3 is to 4, it doesn't matter which way around we write it. Let's match the x on top. So if I've got 4 divided by 3, that's going to be the same as x divided by 2, whatever it is. That's what the theorem says, and that's how we write it together. So the bottom part over the top part on one side is equal to the bottom part over the top part on the other side. So bottom and vice versa. Bottom over the top on one side of the triangle is equal to the bottom over the top on the other side of the triangle. What can we do now? Well, we have two fractions and an equal sign, which means we can cross multiply. If you have another way of solving this type of equation, that's fine as well. Cross multiplication is a nice shortcut though. So I have 3 times x is equal to 2 times 4, which is 8. So 3x is equal to 8, and x is equal to 8 over 3. We weren't given any units, we weren't told centimeters or anything. So that's it, that's all we need to do to work that out. Okay, that's the answer. Okay, we need a definition of a certain type of triangle before we look at the next theorem. Again, if you did higher level maths for junior cert, which I think most of you did, you've already seen this. It's similar triangles. Now, similar triangles are not the same as congruent triangles. They're basically like shrunken versions of each other. So if I have a triangle like this with 3 different angles, and I have a bigger version of the same triangle that has exactly the same angles but different side lengths, then we say that those triangles are similar. So similar triangles have 3 equal angles, but their sides aren't necessarily, they might be, the same length. So if a pair of triangles are similar and they have the sides the same length, then they're called congruent triangles, which we talked about already. So remember when we did congruent triangles, we had SSS, SAS, and ASA. Those were our congruent triangles, and RHS. Those were congruent. If we want similar, it's AAA, 3 angles together. So they're not identical. They can be different sizes, but their angles are the same. Once we know what similar triangles are, we need another definition, which is that there's matching sides. So the side joining equal angles together like this they kind of match up, and I might have equal angles, the one dot one here, the one dot one here. And we have these guys here as well, the third one. Now they're not the same length, but there is something similar about them. So what we say is that they are called corresponding sides. So the blue sides that I've drawn in here, they're called corresponding. So corresponding is the maths word for it. I sometimes just call them matching sides. They're not equal in length, but there's something about them that's important. And we have a theorem, and we say that, let's write down the theorem statement. If two triangles are similar, and let's call them a triangle DEF and ABC, and let's label this one DEF, I can use it as a diagram, and this one ABC. So if two triangles DEF and ABC are similar, then their sides are in proportion in order. In order, what do I mean by that? In order, corresponding sides. Again, we need to know the statement of this. So i.e. DE divided by AB is the same as these corresponding sides one over another. DF divided by AC is the same as EF divided by BC. So basically, an explanation of that theorem, sorry guys, that went off the screen. Here it is. So I can just do this so we can see it all on the same page. The corresponding sides divided by each other will always give me the same answer. So the corresponding sides divided by each other will always give me the same answer. Okay, so this divided by the, move this down again, this divided by this is the same as this divided by this, the same as this divided by this. That's how we've written that down there. Again, you need to learn that theorem. Now we've done a lot, and I'm not going to give you homework on this one, but I'm going to give you homework on the first two theorems. So we'll do an example using this theorem in tomorrow's class. So tonight for homework, I'm going to put the homework up in Google Classroom as usual, but I also just want to remind you that you do need to know the statements and diagrams that go with these three theorems. They're very, very important, and they do get asked. You don't have to prove them, but you do need to be able to state them. Okay, thank you.